So in this lecture we'll cover a little bit more about spectroscopy, and then we'll talk about some other analysis that one can do on chiral molecules. So first of all, let's talk a little bit about two-dimensional NMR spectroscopy. So look at some examples, two examples, one called COSY and one called het core. So it's correlation spectroscopy. So for the example that I've given here, so just for this molecule, so a simple molecule, you would not need COSY and het core to interpret the spectra on this molecule because it's so simple, but it's a good molecule to use just to illustrate the concept how the information that COSY or het core gives you. So basically you do a 2D NMR, so we're going to talk about COSY now. So proton NMR on let's say this is the X direction and the Y direction. So you basically are going to plot the two spectra against each other. So this is all automated on the instrument. So basically what the COSY is going to show you is what signals are coupled to each other in the NMR spectrum. It's an automated feature on the instrument. You just click the COSY button and the instrument will go acquire a COSY spectra for you. So you know the theory behind it's pretty complex. We're just going to look at how to interpret the spectra. So basically, so the signal D is a triplet. Why is it a triplet? Why is D a triplet? Because it's coupled to the CH2, which is the sextet. So if we drop a vertical from D down into here, so if we did the COSY, we would see a peak here. Because that D is coupled to C on the other axis, right? And then similarly C, why is C a sextet? So C is a sextet because it's coupled to both B and D. So C, if we drop a vertical down from C, so C is coupled to D. So we drop a vertical down and then go horizontal over to D. So there would be a peak there. And then C is also coupled to B, so where's the signal for B at? So B is here. Whoops. So there would be a signal there in the COSY spectra. So what else? Okay, so D is coupled to C, we got that, and C is coupled to D, and D is coupled to C, we got that. And then C is coupled to B, so C is coupled to B. So that means there's going to be a signal here as well, right? So B in the spectra at the top is coupled to C, the spectra going vertical. And so if you notice, there are mirror reflections of each other. So you're kind of getting the same information twice. Okay, so what else do we have? So then we have A, but A is not coupled to anything, right? Because it doesn't have any neighbors. So these are what are called cross peaks. For A, there would not be one, so you would not see any signal for it. So doing the COSY, then right away you would see this COSY for this signal A, so you see that there's no cross peaks for it, so you know immediately then the A is not coupled to anything else. Of course it's a singlet also because it's not coupled to anything else. So I don't think I missed anything, right? So that's what your COSY NMR spectra would look like. So it basically tells you why is this a triplet. It tells you what other signal. So it tells you that these two signals basically go together, right? The fact that D has a cross peak with C tells you that C is a neighbor to D, and the fact that C has a cross peak with D and with B tells you that C must be attached to whatever is giving rise to signal D and whatever is giving rise to signal B. And then B sees a cross peak with C. Did I do this? Yeah, B has a cross peaks with C, so it tells you that B is a triplet because it's coupled to whatever is giving rise to this signal. Okay, so hopefully that makes sense. So if you do what's called a het core, so this is stands for heteronuclear correlation. Basically, it's a 2D NMR between carbon-13 and proton NMR. So it's going to tell you what protons correlate to what carbon signals. So if we did this, so D is, you would have a cross peak here. So that tells you that this signal in carbon-13 is due to these hydrogens in the molecule. And C, you then would have a cross peak here. A, let's see, so A would have a cross peak here, and B, cross peak here. So it tells you basically what proton signals in the molecule are correlated to what carbon signals in the carbon-13. So this can help you figure out your proton NMR. If you have some signals that you can't figure it out, but you have your carbon-13 figured out, then that'll allow you to figure out your proton, or vice versa. If you have your proton NMR figured out, but you don't have your carbon-13 figured out, and you don't know what all those signals come from, then you can do a het core. And if you have your proton figured out, then that would allow you to figure out, okay, this carbon C, I didn't know what carbon it's due to in the molecule, but I see it's coming from this signal. And if I know what hydrogens those carbons are on, then now I figured out what carbon that signal is in the carbon-13 NMR. And so then what about E? Well, E doesn't, that carbon doesn't have any hydrogens on it, so it would not have a cross peak with the proton NMR spectra. Right, so you would see there's no cross peak for this, so you know that carbon does not have any hydrogens on it. Otherwise you would see a cross peak for it. Okay, so that's just a couple of examples of 2D NMR, COSY, and het core. The theory again is pretty complex, and it's more useful for very complex molecules when you can't figure out what all the signals are coming from. And there's lots of other forms of 2D NMR. You can do what's called XC, TOC-C, inadequate, HSQC, HNBC. You can do through space correlation. So if you have protons that are not on adjacent carbons, or protons on a not on a carbon, but it's close to a different carbon or a different proton in space, then they can interact with each other, and this type of experiment would allow you basically to get some three-dimensional aspect to your molecule, because you can see what protons it's near in space, even though if it's not attached to those, so it's not technically a neighbor of those protons. There's 3D, 4D NMR experiments. They all get pretty complex. Okay, so that's basically what I wanted to say about NMR spectroscopy. And so the last part of this lecture just focus on other ways to analyze chiral molecules. So since this is a course over organic characterization of molecules, so if you have a chiral molecule, chirality is obviously very important in organic chemistry. One way to characterize chiral molecules would be optical activity. So you talk about this in undergraduate organic chemistry just to make sure you remember it all. So if you had a light source, typically a sodium filament, right, gives off light in all dimensions, all directions, which is what this is trying to illustrate. So light propagating in 360 degrees, all dimensions, right? But it propagates as a wave. So you have light propagating in every dimension, and if you pass that through a polarizing filter, then that polarizing filter, so the light that comes out is plane polarized, so we have light only propagating in one plane now. And then if you pass that through your chiral molecule, then the chiral molecule is going to rotate the plane of that polarized light, right? And then you just measure how much it is rotated. So the instrument's a polarimeter. So light source, again, typically sodium, so monochromatic light, so light of one wavelength utilized. So if we just took a couple of examples, so to remind you of some basic chirality issues as well. So if we take these two alcohols that are chiral, right, this is R2-butanol versus S2-butanol, or sometimes you would see this called +2-butanol or D2-butanol. So those are all, so the R is a stereochemistry designation, right? It tells you that, okay, this is priority 1, that's priority 2, that's priority 3. So using these rules from assigning stereochemistry, forwards and back, so the arrow stays clockwise, so that's the R isomer, right? So that's just a stereochemistry designation. It does not tell you anything about how it rotates plane polarized light. But these symbols, plus and little d, do, right? And minus and L, that tells you the direction that it rotates plane polarized light, either clockwise if it's positive, or D, meaning dextrorotatory, means it rotates plane polarized light clockwise, right? Minus and L means it rotates plane polarized light counterclockwise. But R and S have nothing to do with that. Okay, so these two molecules are enantiomers of each other, right? This is the R and this is the S isomer, so they're enantiomers. And if you remember, enantiomers have the same physical properties: same boiling point, same density, same refractive index, same water solubility. If you took the IR, NMR, mass spec of them, you would get identical spectroscopy out. So that means it's difficult to distinguish between the molecules, right? So how can you distinguish between them? Well, one way is you can measure their optical activity. Right, so this one, the R isomer rotates plane polarized light positive 13.5 degrees, and the S isomer, right, same magnitude but opposite direction, negative 13.5. So what do these symbols mean? So optical activity would typically be reported like this. So the superscript is the temperature the experiment's done at, because the optical activity is going to be temperature dependent. And the sodium D line is what that means, is what was used as the light source. Okay, so just as another example, so here we have a molecule with two chiral carbons, right? So this is S and this is R. So its enantiomer would be SR. So these, of course, are enantiomers, so they would have equal in magnitude but opposite direction optical activity. So these two chiral carbons, 4 possible stereoisomers. So these are the 4 possible stereoisomers, right? So to be an enantiomer, you have to flip every single chiral center. So RS, its enantiomer would be SR. So here, one chiral center is the same and one's different, so they would be diastereomers, and so diastereomers have totally different optical activities, right? So you cannot know the optical activity of this and know what the optical activity of all 4 stereoisomers is going to be. You'd only know the optical activity of what the enantiomer would be. But these two molecules are enantiomers of each other, right? So they have equal and opposite optical activities, minus 10 and plus 10. Okay, so optical activity then is defined. So the specific rotation is whatever you experimentally measure divided by the concentration the sample was at and divided by the path length of the cell, right? Whatever cell was used, whatever that path length is, which of course it should be dependent on the path length, because the longer that light's got to travel through the medium, the more it's going to be rotated. And the more concentrated that sample is, the more that light's going to be rotated. Okay, so path length is then in decimeters, so concentration is typically expressed in grams per mil. So if we took 6 grams of our 2-butanol and diluted it in some solvent to 40 mils, placed it in a 200 millimeter cell at 20 degrees Celsius, so the observed rotation would be 4.505 degrees. So then if we calculate the specific activity, so take what was observed, divide it by the concentration in grams per mil, and convert that to decimeters, then you get the 13.5. And so that's like a fundamental constant for the molecule, right? So long as you did the experiment at the same temperature and same light source, you should get the same degree of rotation. Okay, so optical purity. So this would just be a measure, if it's just R and S isomers, how much of R versus how much S do you have? So you can use the optical activity to figure that out. So that's the optical activity observed divided by the optical activity of the pure enantiomer times 100%. So if you had a mixture of R and S butanol and you measured the optical activity and the optical activity was 9.72 degrees, then you can figure out how much of each enantiomer is present. All right, so you have the 9.72, that's what's observed, divided by the 13.5, that would be what the pure enantiomer, times 100%, so this is a 72% optically pure sample. Okay, so optical purity is the same thing as enantiomeric excess. So that's defined as the magnitude of the D minus the L isomer, how much of each you have, divided by D plus L times 100%. Okay, so D minus L is 72%, that's what we obtained. So D plus L has to equal 100%, right? So now if we add these two together, so we get the L's cancel out, we have 2D equals 172%, divide by 2. So that means the D, there's 86% of the D, so there's 14% of the L. So if you had an 14% mixture of D and L as of 2-butanol, its optical purity is 72%, it would rotate light by 9.72 degrees clockwise. And of course, since there's more of this isomer, that rotation should be positive and not negative, right? If it was opposite, if it was 86%, then it would be a negative 7.2 degrees optical rotation. Okay, so one thing that organic chemists do is try to discover new catalysts that can do optically active synthesis, to do chiral synthesis, to try to make one enantiomer preferentially over another enantiomer. So this is not a synthesis class, so we're not going to worry about synthetically what's going on here too much. But right, if you take an alkene and do a hydrogenation with a metal catalyst, and if that metal catalyst is coordinated to a chiral ligand, then this hydrogen gets absorbed onto the metal catalyst. So now the hydrogen is in a chiral environment. And when this reaction occurs, then you can conceivably get some optical selectivity in your reaction. So with this particular ligand, then you get this optical purity. So you make 57.5% of the S isomer, 42.5% of the R. So if you subtract the two, then you get an optical purity of 15%, which is not great, right? It's not much better than 50-50 or racemic mixture, which is what you would expect if there was no chiral ligand present. Then you would expect to get a 50-50 mixture. So one thing organic chemists do that work in chiral synthesis is try to develop better ligands, for example, that can give you better optical purity. So if they use this ligand instead, then they get a 92.5 to 7.5, so 85% optical purity. Or this ligand, they get 97% optical purity. And so obviously, so what would be one reason that chemists would try to get stereoselective reaction? Well, maybe this is a pharmaceutical agent, right? And if this is a pharmaceutical agent, maybe one of the isomers is useful and maybe the other isomer is toxic or deadly. So you have two choices. You obviously, if one is toxic or deadly, then you can't administer both. So you have two choices: either make one and don't make the other, so then you can just administer the one that is useful. So that would be one aspect of what these type of chemists would do, is trying to develop optically stereoselective reactions that give very high optical purity, or EE, or enantiomeric excess ratios. So then, you know, what level of optical purity is sufficient that you minimize toxicity? But obviously, you know, one aspect would be to try to drive up that ratio as much as you possibly can. Or the other option would be to make both and then separate them. So if you want to separate enantiomers, how do you do that? So really, there's a couple of strategies that you could employ. You could do chiral chromatography, or you could do chiral derivatization, and then that would allow you to do non-chiral chromatography. Okay, so let's talk a little bit about both of these. How do they work? So most times in organic chemistry, you would do chromatography using silica gel, which is non-chiral, which means if it's non-chiral, then you can't use it to separate a mixture of enantiomers. But what you can do is you can derivatize silica gel. So with the chiral material. So one chiral material that's used all the time is cellulose. Why cellulose? One, because it's chiral, and two, because it's extremely cheap, right? There's a whole lot of cellulose in the world. So if you use that as a starting material, and so if you react that with this dimethyl phenyl isocyanate, so basically what happens We don't need to know the reactions here because it's not a synthesis class, but basically the alcohols react with the carbon oxygen double bonds, break the carbon, so this is an isocyanate, reacts with that. So you make a bond from oxygen to carbon, break this bond. This oxygen basically ends up on that nitrogen, and you make this, what's called a carbamate. And then of course you would do that at each of these OHs. So you put a carbamate at each of these. And then what's done is this is absorbed on the silica gel. So now you have this absorbed on the silica gel, and the significance of that is now your silica gel is chiral. And so what you have now is a chiral stationary phase. The downside is it's no silica gel. Silica gel to begin with is not that cheap. 25 kilograms of this cost around $600. And if you do a whole lot of chromatography, you go through a whole lot of silica gel. So silica gel itself is not expensive. And then once you go through the effort to make this and absorb it onto your silica gel, then your silica gel is becoming extremely expensive, right? So doing chiral chromatography is not cheap. But if you want to separate enantiomers, stereoisomers in general, you don't have much choice. You got to invest a little bit of money. Okay, so basically the way it would work then now is you have your chiral silica gel, so pack that into a column, for example, and then put your mixture of enantiomers on it. So you pack your column with the chiral stationary phase, you put your enantiomers on it, and then you start putting some solvent through. And then of course as these start moving down the column, now they will separate. So why are they going to separate? Because in the presence of chiral cellulose, the pairs of enantiomers will form diastereomeric complexes with the silica gel cellulose. And diastereomers have different physical properties, so they will have a different affinity for the cellulose. And so they're going to, so one of the enantiomers is going to stick to the cellulose silica gel a little bit better than the other, so one's going to move faster, one's going to move slower, and so now you can separate them, right? So you collect them in their own separate flask, and now you have them separated. You evaporate your solvent off, and now you have enantiomerically pure compounds. But doing this in a column like that would be extremely expensive because the silica gel with the cellulose compound on it is expensive. So typically this would just be miniaturized. So you could take this chiral silica gel and pack it into a column and do what's known as chiral HPLC, so high performance liquid chromatography. So you take your chiral mixture, inject it onto this column, and push your solvent in right under high pressure, and push that through the column, and collect your sample at the end if you want to. And then typically this could be automated, hooked up with a detector, so that if your compound had a chromophore in it, when it comes off the column, you're going to get a peak, so you know when your samples are coming off the column. So you could do this using what's called an analytical column, or you could do it doing what's called a prep column, which would be bigger. So if you do analytical, you just want to detect the peaks, and so you could use that to determine the optical purity of a sample, right? So you put a mixture on, you don't know the optical purity, but when the peaks come out, then what you can do is you can measure the area underneath those peaks, and you can use that to determine the optical purity, right? So for the percent of enantiomer A would just be the area of A divided by the total area, area A plus area B. And the percent of enantiomer B would be the area B divided by the total area. And then that would allow you, so if you got an 86-14 mixture, for example, if it was 86A, 14B, then your peak A is going to be a lot bigger than your peak B is. Or you could do preparative chiral HPLC. That just means you have a bigger column, but that means it's more dollar. Right, the column's bigger, there's more silica gel, chiral silica gel, and you need a bigger pump, so it just means there's more expense involved. But you still can't separate a whole lot of material. It's still on a small scale. But the upside is that you can run the instrument 24 hours a day. So over time, you could separate a batch of material, but probably not on a kilogram scale though. which if we're talking in a pharmaceutical company, making molecules on a massive scale, this is not an efficient way to separate chiral molecules. So another thing that you could do is you could do chiral derivatization. So if we take these same two alcohols and react them with an acid chloride, so basically what happens is oxygen would attack carbon and kick the chlorine off, and you would make an ester. So in this case, we're using what's called Moser's acid chloride. So the significance is this carbon is chiral, and this would be the 1, 2, this would be priority 1, this would be priority 2, priority 3, so this is the S isomer. And here we have the R isomer of this and the S isomer of that. So we use optically pure chiral derivatizing agent with our mixture. And so when either of these alcohols react, you make the ester in both places, right? But if this is S and this is R, and this is still S, and this is now S, now these two are diastereomers of each other, right? Because this is the RS isomer and this is the SS isomer, and those are diastereomers. So diastereomers have different physical properties. So now you can just use a regular silica gel column. So you could separate the two, but then you have to do a hydrolysis step to cleave off the ester to get your original alcohol back, for example. So that means there's two more synthesis steps involved in your synthesis, but that would be one way to derivatize the two, separate the two, and then get rid of the derivatizing agent. Or you can also use this if you just wanted to know what is the ratio of R to S, so what is the optical purity? Well, the significance being now these two CFD3 groups are diastereotopic with respect to each other. So you could use fluorine NMR to distinguish between the two molecules. So if you did fluorine NMR and you decoupled it from any protons around so that your fluorines just show up as a single peak, then now what you can do is you can integrate the area. So measure the area under the two peaks. And then, so let's say this integrated to 10, this integrated to 1, then you could take area 1, so 10 divided by the total area times 100. So there's 90.9% of this stereoisomer, and then the same for here. Take that area 2 divided by the total area, so there's 9.09% of that stereoisomer. So 90.09 times minus 9.09, so that would be an 81.8% optically pure mixture. Okay, so that's a couple of ways to separate chiral molecules, right? Either do chiral chromatography or make a diastereomer and then separate those two diastereomers and then get rid of the thing that you use to make it diastereomeric. Okay, so lastly, I wanted to talk a little bit about circular dichroism spectroscopy, or also known as CD spectroscopy. Okay, so the theory is pretty complex, so we'll just talk about the theory in very basics. So if we had two waves 90 degrees to each other, and then we added those, and they're in phase, and we added those two waves, so they're equal amplitude and they're in phase, and then add those two waves together, then the resulting wave is going to be plane polarized, and it's going to be tilted at 45 degrees, right? So now if we do the same thing, take two waves, equal amplitude, and they're both in phase, when they enter, and they're going to enter a birefringent plate. And so what happens in this type of plate, so the refractive index of horizontal and plane and vertical polarized light is different. So the two waves pass through this plate at different speeds. So one's going to propagate a little bit faster than the other. And so then if they exit at 1/4 wave out of phase, then what you have now is what's known as circularly polarized light. So rather than light propagating like this, now you have light that's propagating like that in a circularly polarized light. And so it could be propagating like that. So, or it could be propagating like this in the opposite direction. So it's helical, right? So you have helical light here. Okay, so you have, again, what is known as left polarized light or right polarized light. So you have to think of this in 3 dimensions as a coil, or it's helical. So if there was a bead here, and this bead traveled through this coil, and from your perspective, so this would be traveling counterclockwise, so that would be left polarized light. Or if this bead was traveling through the coil this way, then from your perspective, it's going through these coils now clockwise from your perspective, so that's right polarized light. So whenever you make this polarized light, for a CD experiment, you always have right and left polarized light. So you have both. So they're propagating, and one's clockwise, one's counterclockwise. Okay, so now you can use this to do CD spectroscopy. So chiral molecules, which have a chromophore, if you remember what a chromophore means, so that means it has something in the molecule that will absorb UV light. So this is basically just absorption spectroscopy. So if it's absorption spectroscopy, then we're talking about electronic transitions. So electrons then are just going to be promoted from pi to pi star into pi star, for example. So the significance being is that chiral molecules absorb right and left circularly polarized light by different amounts. And so basically what you're going to do then is you're going to have right and left polarized light go through the sample, and the chiral sample is going to absorb right polarized light and left polarized light by different amounts, and so you have what's called a different spectra that results. So you just measure how much of the left polarized light and how much of the right polarized light did it absorb. Right, so so why does it do this? Because if the molecule is chiral, then it's going to interact with the circularly polarized light differently. Okay, so absorption then, so it will absorb, so if you remember, epsilon is the extinction coefficient, so it'll absorb left polarized light and right polarized light by different magnitudes. So you see, so you record a different spectrum, and basically what the spectra ends up looking like, it looks like this. So if you had 1 enantiomer, and you see a CD signal that looks like this, with the enantiomer, its signal would be opposite. It would be same magnitude, but it would be a mirror image of it, and that's basically what a CD spectrum is. So in terms of the importance of CD, so it's very important in biochemistry for the study of proteins. Right, so proteins have phenylalanines, have tyrosines or tryptophans, they have aromatic residues, so they have a chromophore that will absorb UV light. And of course they're chiral, right, because all amino acids are chiral except for alanine. So you have a chromophore and a chiral environment that's going to absorb circularly polarized light, right and left-handed circularly polarized light by different amounts, so you're going to get a CD signal out of that. So the CD spec basically can be used to reveal the secondary and tertiary structure of a protein. The alpha helices, beta sheets, tertiary structure, because that's what's given the protein its 3-dimensional shape, right? So it can also be used to show how secondary structure changes, how these alpha helices, beta sheets, 3-dimensional structure overall changes with temperature, denaturizing agents, pH, different solvents, right? Protein will have different 3-dimensional shape depending on those conditions. And it can also be used to study D to D electronic transitions if there's a metal present. So if there's a metal in the chiral environment, then those D to D electronic transitions are going to be susceptible to a CD, circular dichroism spectroscopy effect. So you could use that, for example, if you wanted to study a metal bound to a protein. Okay, so that's all I wanted to cover for CD spectroscopy, just the very basics of what it is. All right, we'll stop there.